So the next section that we're going to talk about is kind of a general informational section about various different uh, functions that and what their graphs look like and what their domains and ranges are normally, to get you familiar with some of the basic shapes of the graphs and the functions that we might deal with. One thing that we will talk about in this section is a thing called continuity. 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 Continuous functions over an interval. Sometimes that interval is the entire domain. Sometimes they may tell you, look from x being -5 all the way to x being 7. Is it continuous between those two? But a lot of times it's just the entire domain is the interval that they're talking about. Kind of the easy way to think about continuity in a continuous function is that you can draw it without picking up your pencil. Okay, it can be drawn or traced if it's already got a picture there without picking up your pencil. Example of a continuous function. I'm just going to draw a small coordinate plane here and draw a few examples of continuous and discontinuous functions. Copy that. So a continuous function, here's one that's a good example of continuous. I can take my pen and trace that across the entire picture without picking it up. I don't have to pick it up to jump to another spot. This one is continuous. Continuous is what you would call that. Here's an example of one that's discontinuous. Too much space in there. Discontinuous. So when I trace that one, I've got to stop and pick up my pencil to go to the next place out of that. So that's a discontinuous graph out of that. Where they can kind of catch you sometimes is a graph where it looks like it's going to be continuous, but they put this little hole in the middle of it. There's an empty circle there in the middle, and you've got to, when you trace it, you've got to jump over that. So it's an empty spot in the graph. So it is discontinuous because it has an empty space there. So continuous graph, no breaks, no holes. Discontinuous, it's got a break in it, or it might have an empty circle inside of the graph that's a hole. That's considered a hole out of that. So those are discontinuous and continuous. So being able to recognize that is one of the skills in this particular section. The rest of this section is about the basic functions and their names and what they look like and the domain and ranges of those. So we're going to go through those. There are 1, 2, 3, 4, 6 of them that we're going to talk about, and then one of your labs that you'll do for this particular stuff is it has a picture, and you're supposed to match it with. It's like a matching game. You match it with the name of the particular function or the domain that goes with that function out of that. So it's basic information about these basic functions. So we're just going to start basic functions. Sometimes you'll hear these called parent functions. So if you're Googling around for some more information, Basic functions are sometimes called parent functions. So if you don't find what you need by Googling basic functions, you can, parent functions can be it's the same thing, okay? So the first one that we're going to talk about, and I'm just going to call this number one, is the identity function. Identity. I-D-E-N-T-I-T-Y function. The identity function, the equation is f of x is equal to x. The graph is a straight line that goes right through the origin. Get it right through there real good. Looks just like that. Okay. The domain of the identity function is all real numbers. Remember, that's negative infinity to positive infinity. The range of that graph is all real numbers. Again, negative infinity to positive infinity. Okay. It goes right through the origin. That's what you've got to notice. The identity function is a straight line that moves up and to the right. It's an increasing function that goes right through the origin. That's the identity function. It's just the most basic linear equation that we can have out of that. That's what that is. The identity function is the first one. All right. Moving on up to the next one is called the squaring function. Squaring function. And it does just what it says. It takes an x value and squares it. It's the squaring function. It's y equals x squared, or f of x equals x squared is all that is. The graph of that let me do a better job of that. It's too straight. Trying to get it looking a little better. That's better. Looks something like that. Okay. The domain, all reals. Negative infinity, positive infinity. And in its basic form, the range are all y's that are greater than or equal to 0. So the interval for that would be 0 to infinity. That's the range of that. It has a decreasing interval and an increasing interval. It's this U kind of shape here is what that is. I'm going to show you how to graph these with your graphing calculator so that you can kind of use that to help you along the way. So with your graphing calculator, you can hit the top left button, the Y equals button, hit that. And I've already got some stuff in there, so I'm going to clear that out. So you just go to that equation and hit clear, and it gets rid of it. So if any of those that have something in them, you just want to clear that out and get rid of them. Or you can hit second memory and hit 3 and hit enter, and it'll clear everything out that's been entered in your calculator. It's empty. And then I'm going to type in the Y1. I'm going to put that as the identity function. So I'm just going to type an X. To get the X, you're going to use this button right next to the alpha button that has X, T, and then a little Greek symbol called theta and an N on it. We're going to, X is the default for that. Okay. Just hit that button to get X. And if I hit graph from there, I should see that picture that I drew by hand just a little bit ago, the identity function, that nice line out of that. Does anybody not getting that with their graphing calculator. Sometimes there's some things that could cause that to make it, not work. All right, so if everybody's good with that, let's go back to y equals. And then I'm going to, instead of the identity function, I'm just hitting clear to get rid of that. I'm going to get the squaring function. So I'm going to hit x, and then I want to square that. I can either use the squared button right there up and to the left of 7. That gets me the squared. Or I could use the caret symbol to get the squared out of that. And then I'm hitting graph again, and I'm going to see that picture that I just drew. Nice squaring function picture out of that. Okay, so we can see any equation that has f of x equals or y equals, we can graph with our graphing calculator. So we're getting kind of into the basics of learning to do some of that stuff. Okay, so we get the squaring function. We see that picture, nice little picture of that. The next one is the cubing function. So instead of taking x to the second power, it's going to take x to the third power. So f of x is equal to x to the third. And I'm going to use the graphing calculator to draw that picture for me. So I'm going to hit clear to get rid of the squaring function. I'm going to type an x. I'm going to use the caret symbol, which is just underneath clear and above the division symbol. And then I want the third power, so I'm going to type a 3 right there. That's all I want. So I'm going to hit graph, and I see this picture out of that. So it takes this one, we can tell it goes down into the, on the left side and up on the right side there, goes through the origin out of that. So I'm going to take a snapshot of that. Put that on my notes. So you can sketch that picture that we've drawn there. And we get the cubing function out of that. So the domain of the cubing function is all real numbers. Again, that's pretty common here for the basic functions. Again, that's from negative infinity to positive infinity. The range for this one is all real numbers because it goes all, it's on the left side, it's going down continuously all the way to negative infinity on the y direction. So all reals. Again, negative infinity to positive infinity. Easy enough. The fourth one is the square root function. F of x equals the square root of x. Okay, square root of x, we know that there are limitations of the domain for that because that's one of our red flag things, remember from the first section. So we know that there's limitations on the domain and the range. We'll look at the picture of that in just a second. This would be all x's as long as x is greater than or equal to 0. That's the basic graph. If there was something else inside of there, we would know how to solve that. So our domain would be bracket 0 infinity parentheses. That's the interval notation for domain there. Space here. And the range would be y's are greater than or equal to 0 as well. So bracket 0 to infinity. Let's look at the graph of that with our calculator. The graph of that, go to y equals. I'm going to clear out the one I had. So I got nothing there. To get the square root symbol with your calculator, you hit the blue second button and then go down the left-hand side until you see the square root symbol written right above the x squared button, and hit that button, and that's going to get you the square root symbol. And I'm just going to put an x inside of there and hit graph. and I see that picture show up. What that does, it starts at the origin. Paste that back there. Oh, does that? I don't know. It starts here at the origin and goes up and to the right. So that's, our x values start here at 0 and go to the right. So that's toward positive infinity. Our y values start here at 0 and they're going up. Although they're going up slowly, they're still going up. So that's why the range goes toward positive infinity as well out of that. So the square root function is what we're dealing with there. All right. Next one. Same page here. Number 5 is the cubed root function. F of x is equal to the cubed root of x. Let's look at the graph of that one real quick. So I'm going to hit y equals. I'm going to clear out the one I had, and I want a cubed root. There's not to get a cubed root, you've got to use one of the menus in the calculator. So I'm going to hit the math button first. Okay, so I'm in y equals. I'm on y1. I'm going down to the button just below the green alpha button. I'm hitting math, and you'll see other options here. The first one is how you convert from a decimal to a fraction. The second one is fraction to decimal. The third one is the third power. The fourth one is the cubed root. The fifth one is you can do fourth roots, fifth roots, sixth roots. The x there you would fill in. It would give you a box to fill in there with what root you want to take. We're looking at cubed root, so that's option 4. So I can just arrow down to that, hit enter, and I get a cubed root symbol in my y equals. And I'm typing an x, and I'm hitting graph. And what it does is it inverts the cubing function is what it does. And it looks like this. And I'm going to take that picture and transfer that over to my notes. Okay, so nice looking picture. The domain, we can see that goes from left all to the right. It's all real numbers. Again, that's pretty common on the basic functions. And negative infinity to positive infinity. The range, it's the same thing, it's just y's. The y values, all real numbers for that one. Okay. And the sixth one, last one in this particular section, is the absolute value function. And this one kind of came up in one of the labs where you were having to fill in the table and draw the graph for that. The absolute value function f of x is equal to, and it's got these straight up and down bars. Not those in order of operations level, they're the same as parentheses. But what they do is they take whatever numbers on the inside of that and make the answer positive. So if it's a positive 3 in there, then the y value is positive 3. If it's a negative 3 in there, then the absolute value of negative 3 is positive 3. Because it's the absolute value, the definition of it is it's a distance away from 0. And anytime you measure a distance, it's always going to be a positive answer. So it just takes everything and makes it positive is what it does. And the graph of that, how you get that, I'm going to go to y equals again. I'll clear out what I had. And I want to use that math menu again. So I'm going to go down to below alpha, that math button. And I'll take absolute values of numbers. So I'm going to press to the right. And then that first option, ABS, that's shorthand for absolute value. So I'm hitting math, the right arrow key, and then the first option is absolute value. And my calculator has the newest operating system. If you buy one of the color ones, they already have this on there. If you've got one of the black and white ones, if you have, I think it's operating system 2.55 that has the symbols in there. If it just writes ABS parentheses, that's the same thing. You don't have to have the symbols. They just did that for kind of aesthetics, the way it looks. So I'm going to put an X in there and then hit graph, and I see this V shape happening. The absolute value graph is always going to be a V shape. Okay. Always a V shape for the absolute value graph. The domain, all real numbers again. I'm going to copy this. The range, though, we can tell from looking at the graph that the range does not go into the negatives. It is 0 to infinity, or all positive numbers, so y such that y is greater than or equal to 0. So bracket 0 infinity on the absolute value graph, on the basic form of the absolute value graph. Okay. So taking those in, knowing that basic information about those particular graphs. Like I said, there's a lab that's kind of a matching game. It asks you questions about which one of these graphs has a domain that's all real numbers, and you've got to list the ones that have that. And if you look at your notes here, you're going to see, hey, the name of this graph is this, and it's got a picture of that. So it's a pretty straightforward, just kind of a matching game type thing. So, but just basic informational stuff, not a whole lot of work to do in that section. All right, so that's section 2.6. Let us move on to 2.7, which is a little bit more, it's a theory type thing, but it's pretty easy to do. All right, so we're going to talk about graphing techniques, and we'll call them generalizations. The idea of this section is that you could look at an equation and know what it does to a function and recognize that. Not necessarily that we draw the graph based on that, but that we know what it does to the graph and what it does to how the equation being manipulated does something different with the graph. That's the idea. We have a graphing calculator. If we need the exact graph out of it, we can type the equation in there and see it. What we want to do here is be able to look at an equation and just get a generalization of, hey, I know when they had a +3 on the outside there, that moved it up 3. That sort of idea is what this is. It's more of a theory type thing than it is, something that you always do out of that. So we're going to talk about the different things that can happen to an equation and what it does to the graph of that, and then and try to be able to recognize those or perform those operations in order to show that particular graph. So let's start with stretching and shrinking, or the more proper term is compression. For shrinking and compression is the same thing. Stretching, I may be dating myself here, but when I was a kid, we played with silly putty quite a bit. And on Sundays, the paper came and there was always comics in there. and you would take the silly putty and you pat it out real flat, and then you'd lay it on the comics and you'd rub it on there, and then you'd peel it off, and you'd have the picture transferred from the ink. I don't know if anybody else ever did that, but that's what we did, because that was, there was not, Xbox didn't exist at that time and things. So, but the idea of stretching and shrinking is that if you took that silly putty with the picture on it, if you pulled it this way, it would make the picture look skinnier and grow taller, right? So that would be a stretch. And then if you took that and you pulled it this way, it would widen it out and make it look fatter, I guess is the best way to say it. It would spread out. And so Garfield, when you took that picture of Garfield, you could make Garfield look skinny, or you could make Garfield look wider out of that. So that's the idea of what we're dealing with here with these graphing techniques, is a vertical or horizontal stretch or shrink or compression as far as that goes. So let's talk about vertical movements first. So a vertical stretch or compression looks the same as far as the equation goes. You take a function and you multiply by something on the outside. Okay? We're multiplying by something on the outside. If that thing we multiply by is bigger than 1, it's going to be a vertical stretch. It seems to make sense. If you multiply by something bigger than 1, it makes the answer bigger, right? So that would be a vertical stretch. Okay? If that number that you multiply by is between, if A is between 0 and 1, that means it's a small fraction, like 1/2, 1/3, 7/8. If you multiply something by, let's take an easy one like a half, it's going to take it in half, right? So if I take a 4 and multiply it by a half, I'm going to get 2. And if I take, anything that's between 0 and 1 and multiply by it, it's going to make something smaller, right? So that would be a vertical compression. Or shrink. You'll hear me say shrink and compression kind of together. Shrinking, compressing, making it shorter. And when you make something shorter, it kind of spreads it out. It's kind of like the silly putty idea. If you pushed it down, it spreads out on the table or wherever you're working on, right? So, but if you stretch it, you pull it up, it's going to slim it up in the middle there, right? So when you do a vertical stretch, it makes it look skinnier and taller. You do a vertical compression, it makes it look wider and kind of spreads it out some, okay? So that number in the front that you're multiplying by, it's got to be on the outside. Make sure you recognize that it's on the outside. Vertical things happen on the outside. That's one of the things we got to remember. That if it's a bigger number, it's going to be a stretch. If it's a smaller number, it's going to be a compression. Okay. Notice that we don't even address negative numbers here, because that's a whole different thing. Okay. We're just talking about the value of that number. If it's bigger than 1, stretch, smaller than 1, compression. That's what we got to know. All right. So an example of that, of those vertical stretches and compression, you would take like let's take the absolute value function. If we took y equals 2 times the absolute value of x, that's taking the absolute value function and it's taking that V shape that it was, because it's a really iconic shape, and stretching it out. Okay. Doubling its height, basically, is what we're doing. So it's going to make it look skinnier. That's the idea of what we're dealing with here. If we took that same function and did a 1/2 times the absolute value of x, that would be taking that V shape and pressing it down. So when you press it down, it's going to spread the V out further. So it's going to look wider out of that. So that's what's happening here. We're going to mix this in with some other stuff here in a second, but just the general idea of what's happening here. So this is a stretch. This is a compression. Both of them vertical, though, because it's happening on the outside of the function. The function is the absolute value of x. The 2 is on the outside of that absolute value. So that's how we know that it's a vertical stretch and compression. Let's talk about horizontal stretch and compressions. Horizontal stretch, compression, or shrink, whichever way you want to talk about it. Horizontal things happen on the inside. Okay, that's what you gotta think about. Horizontal things happen on the inside. Vertical things happen on the outside. Horizontal things happen on the inside. What we're going to have is we're going to have a function, and we're going to multiply by something on the inside of that function. Okay, instead of our examples, instead of the 2 being on the outside, it'll be on the inside of the bars. That's what we're talking about here. If that number that we multiply by is greater than 1, it's a horizontal compression. It works the opposite way from the verticals. If that number is bigger than 1, we're going to have a horizontal compression. If that number is between 0 and 1, then we're going to have a horizontal stretch. Okay. Examples of that would be, if we're going to have, we take a function. Let's take the absolute value function. So we talked about that with the early one. Instead of putting the 2 on the outside, we put it on the inside. We're multiplying by a number that's bigger than 1 on the inside, so that's going to be a horizontal compression. If we do 1/2 or 1/3 on the inside, and just change up the number, this is going to be a horizontal stretch. These are the things. If you looked at the graphs of the equations, you might not be able to tell this. You can tell this from the actual equations that you're seeing, because there's sometimes you can do a vertical stretch and a horizontal compression, and they'll look exactly the same at the graph level, but the equation level they look completely different. Okay, so we're recognizing it from the equations. Graphs wise, it's really hard to recognize which one's happening, because I could give you a vertical stretch and a horizontal compression that looks exactly the same, but the equations are way different. But the graphs look exactly the same. So it's looking at an equation to find that stuff. All right. Let's look at another type of graphing generalization, and that's a reflection. Reflections are like taking something and reflecting it across an axis. Okay, so if we're going to reflect across the x-axis, if I reflect something across the x-axis, it moves it vertically, because the x-axis is this way, and if I reflect across it, like for example, if I take my a coordinate plane here, there's the y-axis, here's the x-axis. If I reflect this red shape across the x-axis, it moves it vertically down here to that blue shape, right? That's a reflection. So it's a vertical movement. So it's going to happen on the outside. Any vertical movement happens on the outside. The way that it's done is this is where the negative comes in. It's a negative on the outside of the function. For example, like this, this example might be y equals negative x squared. It reflects it across the x-axis. Okay. Across the y-axis is a horizontal movement. So that's going to happen on the inside. So our equation is going to have the negative on the inside. So you might have an example, y equals negative x cubed or something like that. The negative is on the inside. That's how you know it's in a reflection across the y-axis. X-axis is on the outside because it's a vertical movement. Y-axis is on the inside because it's left to right movement. It's horizontal. It's a horizontal movement. Okay. Outsides are vertical. Insides are horizontal. Okay. All right. The next type of transformation that we could have is called a translation. Translation just means left, right, up, or down. Left, right, up, or down. That's what a translation does. It's shifting it left, right, up, or down. So you're just taking the picture, picking it up, and moving it whichever way the equation shows. Okay. So again, the idea is vertical things happen on the outside, horizontal things happen on the inside. So when we take a function, whatever type of function it might be, and we add something to the outside, it moves vertically k units. For example, if we took the absolute value function and we added 3, this plus 3 is a vertical shift up 3 units because it's a plus 3. Same idea. If I took y equals the absolute value of x and I subtracted 5, this minus 5 is a vertical shift down 5 units. Subtracting 5 is the same as adding negative 5. Those are the equivalent operations. So adding on the outside moves it up that number. Subtracting on the outside moves it down that number. Okay. Vertical shifts happen on the outside. Vertical movements happen on the outside. Okay. On the inside, we had y equals f of x plus k. What that does, it's on the inside of the function. So it moves it the opposite direction k units. What do I mean by that? Plus is left, minus is right. On the inside. Okay? Outside is exactly what you see. What you see on the outside is what happens. On the inside, things are different. They're the opposite. Okay? All right, so example, if we took that absolute value of x, and instead of putting the plus 3 on the outside, we put it on the inside, like that. What that's going to do is it's going to move, or it's going to be a horizontal shift left 3 units. It takes the absolute value graph, the V that comes together at the origin, and it's going to move it left 3 spots. That's what it's going to do to it. If we had y equals the absolute value of x, and we put the -5 on the inside, that's going to horizontal shift right 5 units. Inside is horizontal, outside is vertical. Inside is horizontal, outside is vertical. Okay. So, next thing we're going to do is we're going to look at some equations and we're going to decide what transformations have happened to it. What have they done? Have they shifted the original function up, down, left, right, stretched it, compressed it? What did they do based on what we see in the equation without graphing it? Now, we could graph it and try to recognize it, but it's very hard to look at 2 graphs and say, I know they did a vertical shift here, or I know they did a compression or a stretch, because they can kind of trick you a little bit with some of those. Okay, so we're going to look at the equations and do this. So we're going to describe the transformations. This will be example A for the thing. So here's their function. F of x is equal to 3x squared minus 7. Okay. So there are 2 different transformations that are happening to this graph. And just to give you a clue about what we're even looking for here. So we want to look at that and kind of try to find what's going on. What does the -7 do to this graph? Is it on the outside or the inside of the original function? If the original function was x squared, which is what it would be for this one, the basic function would be the squaring function, x squared. What does a -7 out here do? Not 5, but 7 units. Yeah, down 7 units. Because it's a -7, and it's not on the inside with the x squared. It's not in parentheses. So you're going to look for parentheses or the absolute value marks to know that it's going to be on the inside. Okay, so it's down 7 units. Well, there's a 3 in the front here. What does that 3 do to the x squared function? So we're multiplying x squared by a number on the outside. So we know that's going to be a vertical stretch or compression. It's vertical because it's on the outside. It's going to be a stretch because it's a number bigger than 1. And we write that by saying by a factor, vertical stretch by a factor of 3. What multiplier what are you multiplying by? So it tells you if you multiply by 2, it's a different kind of stretch than if you multiply by 3, right? Because they're different amounts. So 3 obviously stretches it more than 2 does. So you just say by a factor of, and then put the number. It's really an easy idea there. All right, let's look at this one. F of x is equal to 1/2 parentheses x plus 4 cubed, and then let's do plus 13. A lot going on with this one. So we got, I see parentheses, I see things on the outside. So I know there's quite a bit going on with this one. This one has about almost everything, not quite everything, but almost everything. So what does the plus 13 on the outside there do? Since it's on the outside, we know it's going to move it vertically or horizontally. Vertical is right. Yeah, vertical because it's on the outside. So I know the 13 it's a plus 13, so it's going to shift it which way? Up 13 units. Change colors here. Up 13 units. What does the plus 4 on the inside do?
Is it a horizontal shift?
Horizontal shift which direction? Left or right?
Left.
Left. A plus is a left 4 units. One other thing to deal with there is the 1/2 that's in the front. Is that 1/2 on the outside or the inside of the function? Outside. So we know it's going to be a vertical something. Is it going to be a stretch or compression?
Compression.
Compression, because the number is what?
Less than 1.
Less than 1. So that's how we know it's a vertical compression by a factor of 1/2. Vertical compression by a factor of 1/2. Pretty easy. Say we had f of x is equal to negative absolute value 2/3 x and then a -8 on the outside. What's this one going to do?
Gonna go down 8.
Down 8. Good job. Are we going to move left or right? Is there a horizontal shift? Is there a plus or minus on the inside of the absolute value? No, there's not a plus, no addition or subtraction on the inside of there. So we know we're not going to do a horizontal shift. So we're going to look at the 2/3 times x on the inside. What does that do? It's going to be a horizontal something. Is it a stretch or compression multiplying by 2/3? Look back at your stretch and compression stuff. If that number is on the inside and it's between 0 and 1, so it's a smaller number, it's going to be a horizontal stretch by that number. Horizontal stretch by a factor of 2/3. One more thing happening. That minus sign that's outside there. What does a minus sign on the outside do? It's going to reflect across which axis? X or Y? If it's on the outside, it's going to go across. It's going to be a vertical movement. So verticals happen on the outside. Horizontals happen on the inside. And be across the x-axis. That's right. Because it's on the outside. If it's negative on the inside of the function, that's across the y-axis. Negative on the outside is going to be across the x-axis. So you want to be able to recognize those. Having those notes handy there can just makes that pretty easy to do. You're not really doing much other than recognizing what's happening there. We're not asking you to do a whole lot of picking up something and moving it a lot. All right. Next thing in this section is talking about a thing called symmetry. Symmetry. When something is symmetric or has symmetry, that means you can fold it across a certain thing and it matches up. So when we do deal with symmetry and functions, we want to deal with that in respect to the x-axis, the y-axis, and the origin. Okay, so if something is symmetric with respect to the x-axis, that means if you take the piece of paper and you fold it right along the x-axis down like that, it would match up and mat up right on against one another. With respect to the y-axis, you fold it vertically and it matches up on each side. Origin, do both. Fold it vertically and then horizontally like that, and it matches up. Okay, so respect to the x-axis is fold it down and it matches up. Respect to the y-axis is folded across. With the respect to the origin, you're going to do both, and it really doesn't matter what order you do both in. Just visualize that if you're going to do that. Now, visualizing it with a graph, you look at the paper, you can actually take a picture and fold it and do that. That's easy to do. With an equation, it's not quite as easy to do. So there are some tests that we do for testing for symmetry for that. And what we're doing, we're going to test for symmetry with equations. Test for symmetry. Find f of negative x. That's what our first step is to do. Okay. The second thing you're going to do after you find f of negative x is if f of negative x is the same thing as the original. That's symmetry with respect to the y-axis. Let's look at an example. Okay. Call this example D. And let's say we had f of x is equal to x squared plus 4. That's the original problem. We want to test that for symmetry, and we're going to test it for symmetry to the y-axis. Symmetry to the y-axis, we're going to plug in negative x and work this out. We got to do a little bit of order of operations stuff to do this. So if I do this, I'm going to get negative x times negative x. That's what negative x squared means. So negative x times negative x would be positive x squared, right? The plus 4 doesn't change because there's nothing that's really doing anything to it, so it's back to plus 4. Is that the exact same as the original? Those are the same, aren't they? So that means this is symmetric with respect to the y-axis. Okay? Symmetric with respect to the y-axis. That is the test for symmetry about the y-axis, or with respect to the y-axis. Okay? Is to plug in a negative x, simplify it, see if it turns back to the original. If it turns back to the original, yes. If it is anything, any piece of it different, then it's not. Okay? It has to match perfectly. If it doesn't match perfectly, then it's not symmetric about the y-axis. Okay? So simple test for y-axis symmetry. Let's look at a test for x-axis symmetry. Okay? This is test for symmetry for the y-axis. That's what that test is. Okay, we're going to use the same example, but we're going to test for x-axis. Test for symmetry on the x-axis. Okay, the test for symmetry for the x-axis is to replace f of x or y with negative y. Solve for y again. Okay, we're going to solve for y again. If, same rule, if f of it, if get back the original, then there is symmetry with respect to the x-axis. Okay. So, example E, we've got the function f of x is equal to x squared plus 4. And we're going to take that and we're going to do the test for symmetry with respect to the x-axis. Okay. So I'm going to put a negative y in the place of f of x. It's a plus 4. How do I get y by itself in this problem, the red one? I'm taking that, I want to get y by itself now. What's really in front of that y? A negative 1, right? How do I get rid of that negative 1? Well, I can't just make it a positive 1. I've got to do some sort of mathematical operation to cancel it out. So what's going on between this negative 1 and the y when they're written like that? They're multiplying, so I have to need to divide that to get rid of it. So I'm going to divide by negative 1. I'm going to divide every single piece on the other side by negative 1. All right. And when I do that, what's it do to each one of those pieces? Changes the sign, doesn't it? Makes that negative x squared. Makes that a minus 4. And is that the original? Definitely not. So this is not symmetric with respect. Okay. If it's not symmetric with respect to the x-axis, it can't be symmetric with respect to the origin. Because remember, the origin is both of them. It's got to, if it's symmetric with the y-axis and symmetric with the x-axis, then it's got to be symmetric with the origin. Okay. So this is one of those cases where, okay, I'm going to do both of these tests and I get the third one for free. That's kind of how that works. All right. Let's look at another problem and see if we can do that. Let's say we had a weird equation like this. X equals y squared minus 3. And we're going to test for the y-axis, and we're going to test for the x-axis, and then we'll get origin for free if it does both of those. Okay. The test for the y-axis is to replace x with what? Negative x. So I'm going to replace the x. I'm going to replace that with negative x. Negative x is equal to y squared minus 3. Okay. And if I try to get x by itself again, just to see if I can get back to the original, I'm going to do the same thing that I did on the previous problem. I'm going to divide by this negative 1 that's here just to see if it'll work out. And I know it's not going to, because that's going to be negative y squared plus 3 then. And that's not the original, right? So this is not symmetric across the y-axis. Okay, so that we know that not symmetric on the y-axis, but it might be symmetric with the x-axis. We got to plug in a negative y, so we're going to replace the y in this case with negative y, and see if we get the original. Well, when I square negative y, that's negative y times negative y, just positive y squared. Is that the original? Yes. So it is symmetric across the x-axis, but not the y-axis. So we know for sure that it's not symmetric across the origin because it's only one of those. If it's yes, yes, it's symmetric across the origin. But if it's no on either of the other axes, it's not symmetric across the origin. Okay. All right. So those tests, for y-axis, put in a negative x. Work it out. See if you can get the original back. The x-axis, put in a negative y. Work it out. Do you get the original back? That's the test for symmetry on x-axis and y-axis. And origin is yes, yes on both the axes. You get origin for free. Okay. Easy thing there. All right. Last thing in this section is odd and even functions. Okay. So it gets a little easier after this section. So odd and even function tests. Odd and even E-V-E-N functions. I'm going to show you the actual test, and then I'm going to show you some shortcuts that can help you do this faster and with a little less having to do a lot of work. All right, so the test is very much the same as your symmetry test. You're plugging in, you're going to plug in negative x or x. Simplify. If there's no change from the original, then it is even. If all signs change, then it's odd. If it is mixed, then it's neither. Okay. So we're going to plug in negative x and try to simplify as much as we can. If it goes back to the original, all the signs stay the same, then it's an even function. If all the signs change, so like everything that was positive becomes negative and everything that was negative becomes positive, then it's an odd function. If it's a mixed bag of that, some of them change, some of them don't, then it's a neither function. There are a whole lot of functions that are neither. There are several functions that are even. There are several functions that are odd. So you're going to get some of all of these as you're doing this. Okay, so we're going to work out some problems, and I'm going to show you using the actual test, and then I'm going to show you a shortcut for each one so that you can kind of recognize it without having to do so much algebra involved there. So it makes it a little easier. All right, so let's. The instructions would say determine if the function is odd, even, or neither. Here's our function. F of x is equal to 8x to the fourth minus 3x squared. The test for even, odd, or neither is to find f of negative x. We're taking negative x and putting it into the problem. That's what that means. So negative x to the fourth power minus 3 times negative x to the second power. Okay. So anytime you raise a negative number to an even power, it turns it positive. So negative 1 to the fourth power is going to be positive 1. And x to the fourth power is just going to be x to the fourth. So that's going to work out to be 8x to the fourth. Same thing happens here. I got negative 1 squared, it's positive 1. X squared is x squared. So 1x squared times negative 3 is still negative 3x squared. Is that the exact same as the original? This one and this one, they are exactly the same. So this is an even function. Look at the exponents. Look at the original. Look at the exponents on the variables. What kind are both of them? 4 and 2 are both even numbers, right? So if everybody has a variable and all the exponents are even, that function is going to be even. Okay? Everybody has to have a variable. Everybody has to have an even exponent. Doesn't matter what numbers are in front. That doesn't matter. It's the exponents. If they're all even, then it's an even function. That's the shortcut to it. Okay? Let's look at this one. Say we had f of x is equal to 6x to the third minus 9x. Again, the actual test is to plug in negative x. And when I work that out, negative x times negative x times negative x is negative x cubed times 6 is negative 6x cubed. Negative 9 times negative 1 is positive 9. What do we notice about this purple one compared to the original? Well, this was positive, now it's negative. This was negative, now it's positive. It's changed the signs of both of those. So that's what makes it odd. The shortcut is, look at the exponents. This one has a 3 exponent. What's the exponent on this x that's beside the 9? It's a 1. 1 and 3 are both what kind of numbers? Odd. So that makes this an odd function. Okay? If everybody has a variable and everybody has an odd exponent on the variable, then it's an odd function. But it's got to be everybody. Okay? One more. Here's a function. 3x squared plus 5x plus 7. Let's put that in there. Okay? If I did the actual test, 3 times negative x squared plus 5 times negative x plus 7. I see, okay, I got 3x squared. That's going to come back the same. This one changes signs, though, and then that one doesn't change at all because it didn't multiply anything. Here we got something staying the same. Here we got something changing, and then we got another thing staying the same. So that's a mixed bag. So this is going to be a neither because it's mixed. Some changed, some stayed. The shortcut is look at the exponents on the variables. I got an even, and then this one has the 1. I got an even and I've got an odd, and then this constant doesn't even have a variable. So if you've got a constant term, a piece that doesn't even have a variable, you automatically know it's neither. Okay, so there's shortcuts to being able to do odd and even, and learning those shortcuts much quicker than trying to do all that algebra that's happening there. So that's why I want to show you those shortcuts that are happening with that. Okay, so we got all this stuff with functions. A lot of things to do with functions. A lot of theory stuff, not so much working it out and getting an answer always. Okay, so big things are the domain, and then all those transformations that we did. So being able to find the domain, knowing those red flags that are existing for that, make sure you know those things. Function transformations, left, right, up, down, stretching, compressing, vertical. Remember, vertical happens on the outside, horizontal's on the inside. And then when we get into this other function stuff, we're testing for symmetry. We're testing for odd and even. We're looking at all the different things as far as all those function families, the parent functions. Remember, learn those and make sure you recognize those. That's going to help you as you build up actually doing things with those functions. So make sure you're paying attention to those. Do we need a break? Because I'm going to keep going today and cover some more material. I'm not going to get out quite as early, but do we need a break today? Or do y'all want to just push through and go? I'll let the group decide. All right. You all right? Okay. Well, we'll keep going then. Okay. So I'm gonna